Okay, so we're back with another example. We just looked at this one, which is a tricky comparison test theorem application. And there's another one right here, which I'll have in the notes that I post. But basically, both of these are tricky in that the inequalities maybe are not obvious. So we're going to look at this limit comparison test, which allows us to get around that. So let's suppose we have two different series, a series with terms called an and a series with terms called bn. They're both positive terms always. And suppose we know that as we go out to infinity, an over bn has a limit of c. What this means intuitively is basically this, that an is equal to c times bn for large n. I should say approximately equal to. In other words, in English, what this means is an is always some proportional size to bn. So if c is 2, then this limit basically means that the an terms are always roughly twice the size of bn. Or if cn is 3, it means an terms are roughly 3 times the size of bn terms. Okay? We're going to assume that c is a finite number. And if that's the case, I should also say a positive finite number, then both of the series have to converge or diverge. So what this means is if one series has terms which are proportional to the terms of the other series, then both series are behaving similarly. They're either both converging or both diverging. Let's think about why this should be the case. So a sketch of the proof, in other words. Our limit being equal to c visually is going to mean this. So here we have our terms an over bn plotted on the y-axis. So if I plug in n equals 1, n is on the x-axis, then I get out an over bn ratio and an over bn ratio. Every time I plug in an n, I get an an over bn ratio. And since the limit is equal to c, yeah, that's saying that as we go out to infinity, the points that I'm plotting must be getting closer and closer to this line. So we see in this picture, the points start off sort of far away from this line, and then they eventually get closer to this line. That's expressing the fact that their limit is equal to c. Okay? And the way I've drawn it right here is c is slightly larger than 0. This is the line right here, the axis right here, is the line y equals 0. So our line y equals c should be slightly above that. So, that's what I've shown you there. We're slightly above the horizontal axis, okay? So what this means is if we think of things like this, is that our terms an over bn, when n is sufficiently large, are always going to follow somewhere in between two positive numbers. And I have on the graph there examples of these positive numbers. So for example, this line, y equals little m is this dotted line, y equals this capital M is this dotted line. So this inequality means that as we get out large enough in the n values, my points should always be plotted between the two lines. So let's see if that's true. So as I go out further here, my points, this point is below this dotted line, so that means this inequality is violated for this point. This point is above the line y equals capital M, so that would mean this inequality is violated. But if we go out, say, past here, then look at all the points. They're all in between the two dotted lines, so this is what we'd call sufficiently large. If you think about it, all we're really doing here with this capital M and little m is restating what's going on with the limit. The limit means these points are getting closer and closer to C. Well, that means if you're slightly below C or slightly above C, well, eventually you're going to be in between those two because we're approaching C. So if we have this inequality, let's rewrite it like this. So I'm going to multiply everything through by Bn, and I see this new inequality. Again, this inequality is true for some m and capital M and large N going out far enough. That's what makes this true. And take a look at what we have there. This is actually the exact sort of setup that we need to be able to apply the comparison test. So that's all we're going to do. Suppose that if we were to add up the Bn terms and get a convergent series, then we would also know that this series converges because these terms, again, you can just factor out that constant. That's a constant. The capital M is a constant. Factor it out. So if this one converges, so does this capital M Bn series. And take a look at this. These terms are smaller than the capital M Bn terms that we have right here. So by the comparison test, our sum of An will also converge because the Ans are smaller than these terms, which make a convergent series. So this is basically what we get by exploiting this inequality. That one right there. And we could do the same to exploit the second inequality, this one right here. Again, if we know the Bn terms diverge, then so will these terms, which are just some constant times it, because these terms are nothing more than little m times Bn. So this guy would diverge if the Bn diverges. And then since we have this inequality, the larger series, An, must also diverge. So remember, divergent series, if you have a larger series, then it also diverges. That's our comparison test. All right, so this allows us to basically make comparison tests in situations that might be a little bit more tricky for the previous comparison test. Okay, this is called our limit comparison test. And the intuition here is that we're talking about two series which have terms that are proportional to each other in size. Even though it might be difficult to find an inequality like this or like this. Remember, that's what we had in our previous example. In this example right here, it was hard to find this inequality. Okay, so next we're going to look at some applications of this theorem, the limit comparison test.